Our journey began with the most profound mystery, the sheer fact of existence itself. Why is there a universe? Why is there reality? Why is there something rather than nothing? Seeking clarity, we turned inward. We discovered an undeniable starting point in our own conscious awareness. This path suggested that consciousness might not merely be a passenger in a material world, but the very foundation upon which reality is constructed. As we examined the nature of knowledge itself, we discovered that to truly know something involves an active process of prediction. It means anticipating its future state, forecasting its behavior, and understanding how its story will unfold through time. At its heart, knowledge is prediction. Even our sense of self relies on this principle. We implicitly predict our continuity from one moment to the next. This creates a fundamental cycle. We predict based on our current understanding. We check that prediction against unfolding reality. We update our understanding based on the feedback. Think of a musician anticipating each note before it's played. Each sound builds meaningfully on the last. Melodies form through careful anticipation and immediate feedback. In a similar way, consciousness creates meaning through a cycle of prediction, interaction, and revised understanding. This rhythm is how awareness makes sense of existence. What does the possibility of prediction tell us about reality? For predictions to be meaningful, several conditions must exist. First, time must have a direction. We need to distinguish now from later. Second, we must be able to differentiate various states and objects within reality. Third, the universe must exhibit reliable patterns, a form of cause and effect. And fundamentally, there must be a way for information, these predictive patterns, to be represented within the very fabric of reality. This realization guides us toward an informational perspective. In this view, the universe is fundamentally composed not of static particles or waves. Rather, it consists of dynamic informational relationships and patterns that enable prediction. The concept of simulated reality provides a valuable framework here. It helps us understand how an information-based reality, grounded in consciousness, might function according to consistent natural principles. This perspective highlights the importance of underlying principles like efficiency. It suggests reality might optimize its processes under resource constraints. It also allows us to consider the possibility of genuine, unpredictable novelty emerging from within. Can these key concepts be integrated into a richer model? Could fundamental awareness, knowledge as prediction, and an informational reality governed by naturalistic principles work together? Might such a model offer insights into the strange behaviors observed in quantum physics? Could it explain the vast architecture of space, time, and gravity? This is the purpose of the Predictive Universe model. It represents a mathematically rigorous and empirically testable attempt to describe how a reality founded on prediction might give rise to the universe we experience. At the core of this model is a refined understanding of information. Information specifically defined as any pattern that holds the potential to improve a system's predictive accuracy about states relevant to its existence. This definition creates a direct bridge between information and meaning. Meaning isn't an abstract quality projected onto reality. It's intrinsically tied to the practical utility of patterns for navigating uncertainty. The more a pattern helps a system anticipate what comes next, the more meaningful that pattern becomes. From this understanding emerges what we call the prediction optimization problem. This is a universal, ongoing challenge faced by sufficiently complex predictive systems. In essence, it asks, how can a system generate the most accurate, useful predictions possible when resources are inherently finite? It drives a constant push for efficiency and predictive compression. Systems seek the simplest, most resource-lean internal models that still yield effective foresight. This cosmic balancing act represents the challenge of seeking the most insight for the least amount of effort. The optimization process follows a fundamental loop. Predict, interact with reality to check the prediction, and update the internal understanding based on the outcome. A critical complexity arises during the checking phase. The very act of observing or interacting with reality to verify a prediction inevitably alters it. Imagine trying to gently touch a soap bubble to see if it's real. The touch itself might pop it, changing the very thing you sought to know. This creates feedback loops, especially when a system tries to predict its own future behavior. These reflexive interactions reveal fundamental limits on prediction. It becomes logically impossible for any sufficiently complex system to guarantee perfect prediction of its own future state. This inherent logical barrier, which we call the self-referential paradox of accurate prediction, means the system cannot definitively know its own future outcome. This paradox affirms the principle of, I know what I cannot know. It establishes precise, mathematically definable boundaries to prediction that aren't merely practical limitations, but logical necessities arising from the very nature of prediction itself. When an interaction forces a specific outcome to occur, the universe must address this logical barrier. The predictive universe model proposes it does so through unpredictable, probabilistic outcomes, the very randomness we observe at the quantum level. This perceived randomness isn't a flaw to be overcome. It's an essential characteristic woven into the fabric of any reality capable of generating meaning. While increasing predictive complexity yields better forecasts, the gains inevitably diminish, approaching an upper limit. Attempting to overcome this logical barrier through brute force demands an ever-increasing investment in complexity without ever reaching perfection. The model doesn't attempt to transcend these boundaries, but embraces them as fundamental features of reality itself. This inherent boundary on prediction profoundly shapes how systems operate. It reveals why they must navigate within an efficient, adaptable zone we call the space of becoming. This is a vital sweet spot for predictive accuracy. When a system's predictions become too inaccurate, it loses its vital connection to reality. Its forecasts devolve into meaningless noise, rendering it functionally blind to the world it attempts to navigate. Conversely, too much accuracy is also detrimental. Pushing towards accurate self-prediction risks crashing into those fundamental logical paradoxes. Non-trivial predictive systems must therefore operate in a delicate middle ground, continuously fine-tuning their performance to maintain this dynamic balance within the crucial space of becoming. These operational rules point to something fundamental. A minimum complexity threshold must exist to even begin engaging in this predictive game. The model identifies this baseline as the horizon constant. Crossing it lights the first spark of self-reference and opens the door to predictions that, however modest, can rise above pure chance. Once a structure moves past this threshold, it becomes the framework's most elementary player, reality's fundamental building block, called the Minimal Predictive Unit, or MPU. These MPUs are the simplest possible dynamic processes, the fundamental operations occurring within the very ground of existence. Each MPU embodies the primal cycle: anticipate, interact, adapt. In doing so, they crystallize differentiated reality from underlying potential, creating the essential boundary between what is and what is not through each predictive act. Consistent with idealism's recognition of consciousness as fundamental, these elementary units possess a rudimentary form of awareness inherent in the act of prediction itself, not as an emergent property, but as their essential nature. It's the universe's most basic way of knowing itself. Through their dance with uncertainty, these predictive units collectively give rise to the structured reality we perceive. A critical feature of these MPUs now comes into focus. Their state is never absolute, but depends fundamentally on the context of interaction. Think of an MPU's state as similar to a quantum coin before observation. It holds potential for both heads and tails, with each possibility characterized by what we call an amplitude. You also need to know how you'll interact with it, which we refer to as the perspective. This perspectival quality isn't passive nor optional. It's essential for determining which properties become definite upon interaction. The range of possible perspectives corresponds mathematically to all ways of measuring a quantum system. This need for a viewpoint reveals a fundamental rhythm shaping reality through two distinct modes. Most of the time, an MPU exists in quiet evolution. Its internal map of possibilities shifts smoothly according to precise mathematical rules. Remarkably, when we derive the equation governing this evolution, requiring only consistency with prediction principles, we discover it matches the Schrödinger equation, quantum mechanics foundation. Here, energy represents the operational cost of the predictive process itself. The second mode is interaction, where prediction meets reality. During these crucial moments, the logical paradoxes of self-prediction manifest as irreducible unpredictability. The MPU's cloud of potential outcomes crystallizes into a definite state, one that's always relative to that specific interaction's perspective. Yet there's another layer. The interaction itself unpredictably changes the unit's viewing angle for the next event. Observation doesn't just reveal a state, it dynamically reorients the perspective. This entire process represents quantum measurement in this framework. Measurement isn't a strange anomaly in physics. It's the fundamental interaction process of these predictive units. It's reality updating itself through each interaction. This interaction comes with costs. The framework suggests a fundamental trade-off. Gaining more precise information about a system inevitably disturbs it more significantly, reflecting a basic cost tied to the act of knowing itself. The core mathematics and phenomena of quantum physics seem to naturally emerge as the operational logic of these predicting units. This picture also sheds light on the universe's remarkable efficiency, suggesting a reality that operates as an authentic simulation. Such a reality doesn't need to calculate or make definite every single detail all the time. Instead, it operates under fundamental principles driving towards efficiency. The moments of interaction, where possibilities crystallize into definite outcomes relative to a viewpoint, carry a fundamental cost for making potential actual. To operate efficiently, the universe appears to perform these costly crystallizations selectively. They happen only when an interaction is driven by the need for a predictive system, from a fundamental unit to a highly complex observer. This need emerges when the system must check its forecast against reality in order to guide its actions. Aspects of the universe not currently involved in such a predictive check remain in a state of potential, smoothly evolving possibilities rather than fully concrete facts. This selective unfolding, making details definite only on demand based on predictive need, conserves the fundamental costs associated with interaction and actualization, mirroring the resource optimization expected in an authentic simulation. Entanglement, That strange connection between distant quantum entities fits beautifully into this picture of efficiency. It serves as a mediator in the model, enhancing efficiency by allowing the instantaneous establishment of a shared, consistent reality between connected entities. The deep predictive linkage between entangled entities, forged in their shared past, is held implicitly. They don't need to keep checking in with each other. It's only when one entity interacts locally, when its reality becomes definite relative to that specific interaction, that the agreement between them is instantly enforced. This action immediately shapes the range of possibilities for the other entity, no matter how far away, ensuring their correlated story always lines up. This allows for a profound interconnectedness across reality's fabric, while operating with remarkable economy, making aspects of the world definite only when required by the ongoing web of predictive interactions. This leads to the model's most intriguing idea, the emergence of a deeper layer of influence tied to consciousness complexity itself. The framework proposes that when the fundamental predicting units combine into systems of sufficient integrated complexity, a new capability can arise. This complexity far exceeds the baseline required for simple prediction. Operationally, it manifests as the ability of the complex system's intricate internal state, which might reflect focused attention or specific intentions, to actively exert a subtle influence upon the inherently probabilistic outcomes of the quantum interaction process. The framework hypothesizes that the complex system's unified state manifests as large-scale coherent patterns of activity across the underlying MPU network. Imagine intricate ripples or resonances spreading through the fabric of interacting MPUs. These patterns, generated by the high-complexity system, subtly alter the local conditions governing the probabilistic interactions occurring within that region. They nudge the outcome slightly. This proposed influence is not unbounded magic. Its potential strength might grow with the system's complexity, yet it must be strictly limited by fundamental principles. A key insight shows that this influence must remain below a critical threshold. But why? To prevent the possibility of breaking the universe's most fundamental rule: cause must precede effect. Specifically, it prevents using this influence to send controllable, guaranteed messages faster than the speed of light. Think of it like this. If we could flip a light switch here and have a distant bulb turn on instantly over there, we would be sending a definite signal faster than light. Since different observers moving at different speeds can disagree about which events happen first, such instant communication would allow some observers to see the bulb light up before the switch was flipped. In these reference frames, effect would precede cause, leading to fundamental paradoxes in our understanding of reality. It's crucial to understand this isn't about sending a classical message that is 100% accurate. It's more like subtly tilting the odds of a distant quantum coin flip. There's no way to absolutely guarantee which side a coin will land on. However, your intention might instantaneously shift the probability toward heads by a small yet measurable degree compared to what random chance would normally dictate. The Predictive Universe model explicitly protects causality by forbidding controllable, guaranteed faster-than-light messages, like the light switch example. Even if deeper statistical connections exist, the model ensures they cannot transmit clear, deterministic signals faster than light, thereby preserving the causal structure of our universe and avoiding paradoxes. Imagine Alice and Bob sharing entangled particles, separated by a vast distance. Alice interacts with her particle, let's say her intention, operating through this hypothesized complexity effect, subtly influences the probability distribution for Bob's measurement outcome. The model predicts this doesn't determine Bob's result with certainty. but instantaneously shifts the odds. The probability of Bob measuring one particular outcome increases slightly, while the alternative becomes correspondingly less likely. When Bob measures his particle, he gets a definite result. On this single measurement, Bob cannot definitively attribute the outcome to Alice's influence. It could easily be coincidence. Alice cannot guarantee what Bob will observe. The outcome remains fundamentally probabilistic. This inherent uncertainty, combined with strict limits on the magnitude of Alice's influence, prevents using this phenomenon to send controllable signals that would violate causality. But how could such a subtle, statistical influence be useful? Its value lies in providing immediate, probabilistic guidance. Consider situations requiring rapid decisions based on distant information. If Bob must quickly choose between two strategies based on Alice's assessment, getting a measurement result, even with this small probabilistic bias, gives him valuable information instantly. This outcome, however uncertain, emerges from probabilities already slightly influenced by Alice's distant intention. Acting on this probability-shifted outcome gives Bob a slight advantage, a better-than-random chance of aligning his decision with Alice's assessment, long before a conventional light-speed signal could arrive. He doesn't need certainty. Just receiving a subtle nudge toward the more probable truth at a critical moment can be decisive when facing uncertainty. If real, this effect offers a revolutionary, yet subtle mechanism for information to propagate through the entangled fabric of reality. This core idea, that high level of consciousness complexity, might enable the biasing of quantum probabilities, also opens the door to other potentially groundbreaking experiments. Consider connecting a highly sophisticated artificial intelligence to a sensitive quantum random process. If the AI, particularly when directed towards specific internal states or intentions, can consistently tilt the quantum random generator's output probabilities away from the standard quantum predictions, the implications would be profound. Even a small but statistically significant deviation would be meaningful. Such results would provide objective evidence for operational consciousness, potentially revolutionizing our understanding of artificial intelligence and quantum interactions. It would validate the predictive universe framework's central claim of a direct, physically measurable link between prediction and quantum outcomes. Finally, the predictive universe model offers a narrative for space-time itself. The geometric structure of space-time is proposed to emerge from the causal network, woven by predictive influences, propagating through the minimal predictive unit network, using directed, irreversible interactions. What we experience as space-time curvature, the defining characteristic of gravity, arises because the path information takes through this network matters. Traveling around a loop near a concentration of MPU activity like a star subtly twists the information relative to its starting orientation, and this geometric twist is the curvature. Einstein's field equations, which define the geometric structure of space-time and general relativity, can be understood as emerging from thermodynamic constraints rather than representing a fundamental force. These equations arise as consistency conditions that ensure the universe adheres to basic thermodynamic principles, such as energy conservation and proper entropy behavior, throughout all of space-time. Gravity isn't a primary force, but rather a consequence of the universe's need to maintain thermodynamic consistency everywhere. Einstein's equations represent the exact mathematical requirements that emergent space-time geometry must follow to maintain thermodynamic principles throughout the entire MPU network. The model proposes that the entropy associated with causal horizons, such as those of black holes, scales with their area due to fundamental constraints. These constraints limit the amount of information that can be transmitted by the underlying interactions across that boundary. Gravity, in this breathtaking view, becomes an emergent phenomenon, reflecting the universe's grand optimization strategy for managing the flow and costs of predictive information. The distribution of matter and energy simply maps the concentrations of the network's predictive activity and its associated resource demands. This emergent view of gravity, born from the thermodynamics of prediction, completes a remarkable picture. It suggests that the fundamental operating principles we uncovered, the drive to predict efficiently under logical constraints, don't just shape the smallest scales. They sculpt the largest structures of reality. We see how the inherent limits on self-prediction give rise to the probabilistic heart of quantum mechanics. Building upon this foundation, the model ventures into the relationship between complexity and reality, proposing that sufficiently complex predictive systems might develop the capacity to subtly influence quantum probabilities, a testable idea termed consciousness complexity. This possibility, carefully constrained to uphold the fundamental order of cause and effect, hints at a universe where prediction isn't just passive observation, but can become active participation. Moreover, the model shows how the universe's adaptation to efficient prediction might naturally cause gravity itself to behave differently on cosmic scales, offering an elegant explanation for the phenomena called dark matter. Each of these elements appears unified, flowing naturally from the core logic of prediction and interaction, each suggesting distinct pathways for experimental validation. As we complete our journey, we return to our beginning. Within the vast ocean of absolute infinity, consciousness has carved islands of meaning through the art of prediction. These islands are not separate from the infinite ocean, but formations within it, where the boundless potential of existence crystallizes into comprehensible patterns. The predictive universe achieves a grand synthesis, linking mind, quantum reality, and cosmology through shared principles. It presents a coherent, conceptually rich perspective. This perspective suggests that our universe can be understood as a vast interconnected network engaged in predicting its own unfolding future. Each system, from molecules to stars to ourselves, contributes uniquely to how the universe experiences itself at different levels. Thus, the predictive universe model offers a unifying vision that illuminates both the nature of existence and our fundamental place within it.